This lecture we are going to cover shear stress analysis of the beam. Right? In previous analysis of beam, we have considered the case of uniform bending where shear force along the section is zero and bending moment is constant over the section, right? But in most of the cases, beam is always subjected to non-uniform bending. Non-uniform bending suggests there will be the variation of bending moment along the length of beam, and there will be the variation of shear force along the length of beam. Before going through the detailed analysis of shear stress, we will consider an example of a beam, that how shear stresses are generated in the layers of beam. Consider there are three layers of beam piled up together. I say this is the three layers of ply, they are piled together, right? Here in this case they are in unloaded condition, but when the load is applied onto this beam, what will happen? They will be deformed, and this deformation varies from top layer to bottom layer, right? At the same time, what we see that there is the sliding of layer at the interface of each layers, right? That means layer 1 slides over layer 2 or layer 2 slides over layer 3, right? And we know that when there is sliding of one plane against another, then there will be the shear stress, right? Then there will be shear stress in the beam. Here, right? Here I have written it that shear stress involves the sliding of one plane against another, and this shear stress always try to retain the transverse section of beam. This shear stress always tries to retain the shape of transverse section of the beam. Clear? Right? So we can say that in the beam, the stresses that keeps the layers together, are shear stresses. I have made a say that suppose here is a section, a segment, right? Here beam is unloaded condition. If we make a diagram here, then there is a rectangular cross section, right? Then it is not a cross section. The shape is of rectangular, right? But here what we see that if we take a section here at between these two interfaces of 1 and 3 with 2, then there will be sliding at this layer and there will be sliding at this layer, and this sliding causes shear stresses at the interface, right? Suppose this shear stress is in this direction, and here it will oppose in this direction, right? Now we know that from the static concept of a static equilibrium that if two shear stresses are set up in the beam, then these shear stresses will try to rotate this segment in clockwise direction, right? To oppose this shear rotation of clockwise rotation, there will be an opposing rotation set up by the beam itself against this, and this shear stress is known as complementary shear stress. Already we have studied it in the concept of complementary shear stress when we are studying stress analysis, right? Now Why we are studying shear stress in the beam? Why it is important? Why it is important to study shear stress in the beam? This one we can understand from this figure, right? These two shear stresses, right? We generate a resultant shear stress, resultant stress in this direction, resultant stress in this direction, and these two shear stresses will generate a resultant stress in this direction, right? These two shear stresses will be equal and they are opposite to each other. So generally they will create a normal effect, normal stress effect in this direction. Clear? In this direction they will create a normal shear stresses, normal stresses here, right? And resultant of these four stresses will create a pull effect on the segment. This force, this stress and this stress, they are putting the whole section under tension along the diagonal of segment, right? So we can say that this segment will shear off, this segment will tear off, this segment will break off along this cross section that will be the 45 degree from the axis of, at 45 degree from the axis of the segment. Generally this type of failure occurs in brittle material, right? Suppose our beam is concrete. Here I have taken the example of concrete beam, right? This is our concrete beam. And generally we have seen that concrete beam fails, right, in 45 degree to its horizontal longitudinal axis, right? And why they are being failed? Because due to the bending of beam, shear stresses will be set up in the layer of the beam, and this resultant of this shear effect is of pull effect, at 45 degree, is a pull effect on the plane at 45 degree to its axis, right? And 45 degree to x axis. Due to these stresses, this fails, concrete beam fails along this cross section, right? So that's why it is important to study the value of this net shear stress set up in the beam, right? And here what we see, that tau dash is coming to oppose the effect of this tau, right? And resultant, if these are happening in the section, obviously these two will be generated. In the analysis, it is not important to analyze these two stresses. We will focus on to determine the formula for this value of horizontal shear stresses. These shear stresses are our concerning points, right? Now we will derive a equation, a formula for the horizontal shear stresses set up in the beam due to the bending. Clear? Now, before going for deriving formula for shear stresses, certain assumptions are made, right? These assumptions are that shear stresses acting on a cross section are parallel to the shear force acting in that particular section, right? Or parallel to shear force acting in that particular section, right? If make a 3D element of beam, then stress, shear force, load always act normal to the surface. then shear stress is generated will be along the cross section. This is written here, shear stress acting on cross section or parallel to the shear force acting in that particular section, right? So these forces are along the cross section, they will create a shear force in this direction. In the same, along these lines, shear stresses will be generated in the beam. Now shear stresses are uniformly distributed across the width of the beam. They vary along the depth of the beam, right? Further we will discuss it in detail. And there should be variation of bending moment along the length of the beam, right? Because we know that in case of uniform bending there is no shear stress set up in the beam, right? Shear stress will be analyzed. Shear stress will happen in the beam only in the case of non-uniform bending, when there is the variation of bending moment and shear force across the length of the beam, across the section of the beam, to remember. Now we'll go for the formula, derivation of the formula, right? Here I have written the definition of shear stress which is occurring in the beam, right? In the beam during bending, stresses that keeps layer together are known as shear stresses, right? Clear? Now for the deriving formula for shear stress equation or shearing equations, right? Consider a beam. This is our beam, and we have considered a small length dx for the analysis of the shearing equations, right? Now this length dx is under observation. Length is a b, length is dx, and portion is a b c d. Cross section of the beam at portion AC is ACEG. G is hidden, and cross section at BD is BDFH. BDFH, right? This is neutral axis, and here horizontal centroidal axis along the horizontal longitudinal axis will be the neutral air line, right? Say beam is simply supported and subjected to UDL, right? Consider example of concrete beam. Concrete beam which is of rectangular cross section, have width and depth, and it is always having the weight of roof which is uniformly distributed across its width, right? Now I have made an enlarged view of this portion ABCD here. So this is the enlarged view of portion A, B, C, D, right? A, B, C, D. This is the neutral layer line, right? And now consider a layer RS at distance Y from this neutral line, right? Neutral layer line. And shear force acting at AC is V and BD is V plus dV. Already in assumptions we have made a requirement that we will derive a shearing equation for non-uniform bending cases, and for non-uniform bending cases there is the variation of shear force and bending moment, right? At AC moment is applied M, and at BD say bending moment is M plus dm. Length of beam is dx. Now we will find the value of shear stress at layer RS of the beam, right? This is the bending stress, a variation of bending stress across the section of the beam, right? Bending stress is maximum at outermost fiber, right? It is maximum here and here. Similarly, and here at this portion BD, the bending stress is maximum at outer fiber here and here. Clear? Now right, now watch these two figure very closely. Clear? These two figure very closely, right? What I have made, for the ease of understanding, clear? This is a portion A, B, C, D, right? And here is the layer RS. I have made a cross-sectional, 3D cross-sectional view of layer RSCD, right? Layer RSCD, cross-sectional view of this layer, right? RS along the width, it is RSTU. And RSCD, we are watching it from front side. This is RSCD, and along the width, this is RSTU. Clear? And width, length of the beam for observation is dx. Clear? Now what happened? Due to the bending moment M, bending stress set up in the beam at this portion RC is sigma 1, right? At this portion RC is sigma 1, and due to the bending moment M plus dm, bending stress set up in the beam at this portion ds, is sigma 2, and due to these two bending stresses, what happened? There is the sliding of layer, right? Here we are watching from C to R. When we are moving from C to R, the layer close to C is extended, and layer away from C is less extended, right? That means there is the sliding between the layers. Clear? Similarly, here what we see, that due to this sigma 2, due to the bending stress set up by M plus dm, layer close to D has higher extension in comparison to layer away from the C. Clear? And we know that why here it is higher, because bending stresses is maximum, and when we are moving from topmost to neutral axis, then it is start decreasing, right? If it is decreasing, that means there is the sliding of layer between these two, right? That means this layer is sliding over this layer, right? Similarly, this layer is sliding over this layer, right? And due to the sliding of these layers, there will be the shear stress set up in the beam across this layer RS, along this layer RS. So now bending force, net force set up by this sigma 2, if the area of this portion, this segment RSCD, if the area of this segment RSCD is dA, right? Say the area of this portion SUDH is dA, right? dA SUDH, the area will be B, and this depth will be equal to D by 2 minus Y. Then area, what will be the area of DSUH? B into D by 2 minus Y. And due to this bending stress sigma 2, right, bending force set up in the beam will be normal to this section, and this is say F2. Similarly, at face cross section RCTV, the bending force set up in the beam is F1, right? And due to the sliding of layers, shear stress set up in the beam is SF. Shear force set up in the beam is SF, that acts along the layer RS. Now, if you are considering static equilibrium, then the net force acting on the beam, acting on the layer RSCD, acting on the segment RSCD will be 0. Then F2, that is net force on the segment DS, due to bending moment M plus Tm. F1, this is net force on the segment CR, right, CRTV, right? Sorry, CRTG, clear? CRTG due to bending moment M, clear? And net shearing force set up along RS. SF, what is SF? SF is net shearing force set up along RS due to sliding of layers. Due to sliding of this layers, right? Due to sliding of layers on one and another. Clear? This will be equal to 0. Now I have given the detail here. This F2 will be equal to sigma 2 into dA. F1 will be equal to sigma 1 into dA. Right? Clear? This we can write here. This segment ds will be DSUH, and this segment CR will be CRTG, right? CRTG. Clear? We can say, and SF will be RSTU. RSTU acting along this layer, right? Clear? So sigma 1 into dA will be for F1, and shear force, for shear force will be the shear stress acting along the surface RSTU, then width of surface is B, right, and length is dx, then surface area will be B into dx, shear stress developed is tie, and surface area for this RSTU is B into dx. So tau into dA, here dA is equal to B into dx, right, equal to 0. Further simplify this equation, what we will get, that here we see that our y here for the limit of dA, right, dA will be B into dy, right, B into dy. So then what we see that this limit is varying from y here. Y is varying from, sorry, for portion RSCD, it is varying from y to d by 2. This length is total d by 2, and this layer RSCD, we are going to calculate shear stress value for RSCD at layer RS. Then the value of y is varying from, clear, dy from y to d by 2. We will put the value here at integration term, clear. This is y2 dy 2, and sigma is replaced by bending equation formula, m plus dm, m upon I into y, m plus dm upon I into y. This is sigma 2. This will be equal to, this whole term is equal to sigma 2, and this is equal to sigma 1, and tau into b dx equal to 0. Clear? Now tau into b dx equal to dm upon I, because m upon I y into dA and this one, they will be cancelled out. What left? dm upon I, integration of y into dA. Now dm by b into dx, transfer over here, then dm by dx 1 upon ib y into dA. This y into integration of y into dA is known as the first moment of area of segment RSCD, about neutral axis, or neutral line, neutral axis. Clear? And it can be represented by q, then, and dm by dx, and this dm by dx is the shear force, because we know that rate of change of bending moment with the distance, with the length of the beam, is known as shear force, and this is V upon IB into Q, where Q is the integration of y into dA, and in this case here dA varies for y to dy2, and it is also, we know that this one is equal to A into y bar, right? This is, if we add here, if we remove it by algebraic summation, then it will be sigma aiyi, and it will be equal to A into y bar, where y bar is the location of centroid of the given segment, segment under analysis from the neutral axis. Clear? From the neutral axis. And here I have written Q is the first moment of area of given segment RSCD about neutral axis. Now we will go derive, further simplify this equation for this given rectangular cross section of the beam. Clear? Now here I have made the cross section of beam BDFH, right, at the portion BD of the beam. Clear? Be very clear. It is quite, this figure is quietly related to previous one, right? Here A C E G B D B F H, right? So I have made a cross section view at DB. Then what will happen? DBFH and S is lying here, right? S is lying at the portion DB, and counterpart of S to that side is U, right? Here this portion will be replaced by DBFSU. Clear? Because SU line is at distance Y from neutral axis. Clear? Where is the neutral axis? Neutral axis is this line. Clear? This line. If we make this portion DBFH, right, along with this S, and we know that the cross sectional view of S is here, DSUH, and extend it over open up to B, and on that line will be F. Then the cross section will come at portion DB will be DBFHSU. Now SU is at distance Y, we know that. We will calculate the value of tau, right? For this distance, already simplified that. Tau is equal to V upon IB into Q. Now put the value of Q into this equation. Put the value of Y in this equation. Now we know that Q is equal to A into Y bar. Q is equal to A into Y bar. Now I is the moment of inertia of this section SDUH about its centroidal axis, right? Sorry, I is the moment of inertia of this rectangular cross section about the neutral axis, and V is the shear force generated at this portion. Then V into B, and I put the value of I is BD cube by 12, and B is given. A will be equal to, for this segment, A will be equal to width into depth. Depth for this portion is D by 2 minus Y. This is, and Y bar will be this distance. Up to this is Y plus half of this distance. Half is D by 2 minus Y by 2. Then Y plus D by 2 minus Y by 2. This is half of this distance. Right? Simplify it. Then when simplify, we find that tau equal to 12V upon BD cube into D square by 4 minus Y square upon 2. Clear? Now from this equation, what we see that this value will be maximum when Y is 0. When Y will be 0, then put the Y0 into this equation, then tau max will be 12V upon BD cube into D square upon 8. Simplify it, what we get? Tau max equal to 3 by 2 into V upon BD. V upon BD, where V upon BD is equal to shear force upon area, surface area, right? It is equal to average shear stress generated on the beam cross section, beam segment, right? This will be equal to tau mean. Then tau max is equal to 3 by 2 into tau mean. Here I have shown the shear stress variation for this section. Right? Tau max and tau, because we know that for the top layer there will be no sliding, so shear stress is 0. At top layer of the beam there is no sliding, right? So shear stress is 0. And in meanwhile layer there is the sliding between the layer, so there will be the value, right? There will be the value of shear stress. Clear? So this is the concept of shear stress generated in the beam due to the non-uniform bending of the beam.